The question was asked, what are the main differences between the intracellular and extracellular acid-base buffer systems, and which one is more effective during exercise?
Intense exercise. Let's start with the intracellular. The most common buffers for intracellular are proteins, phosphate groups, and bicarbonate. Intracellular phosphocreatine is a useful buffer at the onset of exercise, which is important to know. And there's not really many components about intracellular, but there is a lot about extracellular, so we're going to move into extracellular now. Extracellular, their primary buffers are bicarbonate, hemoglobin, and blood proteins. Blood proteins act as a buffer in extracellular, obviously you just said that. They contain the most important one of the three buffers in extracellular is hemoglobin. It's majorly or mostly used at rest, and it has two different components, deoxygenated and oxygenated. Deoxygenated is a better buffer because it binds better to hydrogen rows. Hemoglobin can't minimize pH changes because of CO2 loading. The bicarbonate buffer of the extracellular side, but there's also intracellular bicarbonate also, but both of them result in some sort of improvement in performance and some exercises, and Tim's going to get more into that, and he's going to talk about the similarities.
The similarities are that both contain ionizable groups that are weak acids that act as buffers. Because blood proteins are found in small quantities, their usefulness is not very good. It's pretty limited. Blood proteins with the extracellular are very similar to proteins in the intracellular. The question was which one of extracellular versus intracellular is more effective during intense exercise. This question doesn't relate as well with intracellular versus extracellular due to the many parts of each component of buffer system. The intracellular buffer bicarbonate, along with the extracellular bicarbonate, are the most common buffer system within any type of exercise. Intracellular is more with the onset of exercise, and then extracellular is within just any type of exercise after that. But that is all within the bicarbonate. Hemoglobin is more during rest with the extracellular, as well as the proteins for both intracellular and extracellular.
Moving on to our next question. Let's see here. By having more aerobic days, say 3 days, than anaerobic days, say 2, in weekly training, would the body convert the fast-twitch muscle fibers to slow?
Well, it's well known that as endurance training continues, the slow muscle fiber type increases. The fast-twitch muscles are converted into, or there's a shift from fast-twitch to slow-twitch muscle fibers. The shift occurs because there is a reduction of fast myosin in the muscle. This then correlates into a rise with the slow-twitch muscle fibers, the slow myosin within the slow twitch. The shift is needed to create a more mechanically efficient physiological myosin isoform. This is needed in order to improve the endurance performance, and this is an ideal aspect to it.
Something else about the shift. Shift will depend on the individual's training intensity and the duration of training. It'll play a factor along with the total number of years the individual trains with endurance activity. Over the course of several years, type 1 muscle fibers or slow twitch will increase due to training-induced endurance exercise.
As this kind of correlates, it doesn't necessarily mean that all fast twitch muscle fibers will convert or switch over to slow twitch. Even in highly elite athletes, it is only possible that they can have a large number of slow twitch muscle fibers by genetics. So they will be genetically gifted in order to have a large number of endurance slow twitch muscle fibers.
The end.
Good job.